Sometimes it's really important to know how far away from the mean a random variable tends to get. What's an average distance away from the expected value? So let's consider a discrete random variable x with mean mu. Here's sort of something you might think of. You might say, well, what is an average? What's the expected difference between a random variable x and its mean mu? You might start here. There's a problem with this. Sometimes x will be above average. This difference will be positive. Sometimes x will be below average. This difference will be negative. And it turns out that every single time, this mean is equal to 0. One way to fix that is to make every one of these deviations between x and its mean count in a positive way by squaring. That's a way to make every deviation from the mean count positively. The squaring kills off any of the negatives. This quantity is known as the variance of x. It turns out that this definition is sort of intuitive, but it's kind of a pain to compute with. So it's lucky for us we have an alternate definition or an alternate formula. You can find the variance of x by finding the mean of x squared and subtracting the square of the mean of x. Sometimes people call this the second moment of x, and this the square of the first moment of x. Very useful formula. Final thing to mention is that the variance of x, it has a lot of nice mathematical properties, as we'll see later on, but it's kind of not measured in maybe our favorite units. If x is an amount of money, look, we've squared everything. We've just reported something in square dollars, or square euros, or square British pounds. And I don't really know what those look like. You can't pay for them, pay for stuff with those. So at the end, we can fix the units by taking a square root. We use the symbol sigma to stand for the standard deviation of x. And the definition of sigma is it's the square root of the variance. That does the job of fixing the units. Where if x is in dollars, variance would be in square dollars. Sigma is a Greek s for standard deviation. Sigma is now back in dollars. For this reason, this relationship between sigma and the variance, oftentimes the variance is denoted sigma squared. And we'll see an example involving variance and standard deviation right away here. Let's use this next example to see how to compute variance and standard deviation for a discrete random variable, and to introduce a bit of language that commonly is used when people are talking about means and standard deviations. A random variable x has the probability mass function in the table below. We want to find the variance and standard deviation. Variance means that we'll always use this formula where we take the expected value of the square of x. That quantity is called the second moment of x, and we'll subtract the square of the mean of x. I like to find the mean itself first. We're going to need to find e of x as well as e of x squared. To find the expected value of x, we're going to need to take the values for x. I'm calling the values themselves lowercase x's. And we have to multiply those by the probabilities. X times the probability that x lands on that line in the table. So 0 times a 0.4 is 0. 1 times a 0.2 is a 0.2. Multiply here, you get a 0.4, 0.3, and a 0.4. When I add these products together, I get the mean. And here are notations for the mean. You could write e of x, you could write mu. Those add up to 1.3. We also need to find the second moment, and to do that, we're going to just scale the values for the squares of these x values, scale those by how likely you are to encounter a particular x coordinate. So just over here to the side, I'm going to jot down, I usually jot these down. 1 squared is 1, 0 squared is 0, just to keep myself from making mistakes, so I'll show you what I do. 4 squared 16. And now I'm going to take these numbers, I'm going to take the 0 times the 0.4, and I get 0. Take the 1 times the 0.2, and I get a 0.2. Take the 4 times a 0.2, and we get a 0.8. The 9 times a 0.1, we get a 0.9. 16 times a 0.1, we get a 1.6. And when we add all of that together, we get 3.5. That quantity is the expected value of the square of x. So the variance of x is, we take the 3.5, the expected value of the square of x, and we subtract the square of the mean. And when you do that, you're going to get 1.81. The standard deviation for x, we write sigma for that, it's the square root of 1.81. And that's roughly a 1.345. As a check, remember the definition of variance, not the formula we use to compute it, but the definition, it's the expected value of the square of some differences. The expected value of a square can never be negative. So if you subtract and you get a negative, you know you've got a computational error somewhere. In part B, find the percentage of the time that x takes a value that is within one standard deviation of the mean. That if you think of a number line, and you think of some point on the number line being this mean, which was 1.3 in this case, instead of making little marks every 1 unit, we could make marks in sort of standard deviation units. View it as sort of go sigma units to the right and sigma units to the left. Let's see, so this would be 1.3 plus that standard deviation, 1.345, which is a 2.645. Over here, this point on the number line, this point would be the mean, and we've scooted to the left, 1.345. The mean minus the standard deviation, and we get a negative, a negative 0.45, a negative 0.045. Being within one standard deviation of the mean means being within this interval. You could talk about being within 2 standard deviations of the mean if you wanted to. You could go another standard deviation over here and another one over here. And being within 2 standard deviations of the mean would mean being within this even wider interval. So when we see this question, find the percentage of the time that x is within one standard deviation of the mean, or an equivalent question, find the probability that x is within one standard deviation of the mean. It means this. Find the probability that x lands between, if I start at mu and scoot left 1 sigma unit, or start at mu and scoot to the right 1 of these sigma units. How likely is that to happen? Let me erase this going an extra sigma. That was an illustration that we're not doing now. Okay, well this quantity here was a negative 0.045 when we performed that subtraction, and this was a 2.645 when we added that together. Which values of x fit within that interval from minus 0.045 up to 2.645? Well, the 0, the 1, and the 2 are in that range. This is an equivalent question in this particular example to saying how likely is x to be a 0, a 1, or a 2. And we could just add the probabilities that x lands on one of those values, 0.4 plus 0.2 plus 0.8, plus 0.2. It's a total of 0.8. That is to say, 80% of the time, this random variable will produce a value that is within one standard deviation of the mean of 1.3.